we were discussing. So as we have seen this problem from last, I think, couple of classes. So there is only v velocity. So there is a momentum is there only in z direction. So this second suffix indicates a direction of momentum. Okay. So this is z momentum. So it has a three component. So this z momentum flowing in z direction, which will be given by rho vz into vz plus pressure into tau zz. Okay, and this is z momentum, how it is transferring in x direction. How z momentum is transported in x direction, that will be a rho vx into vz plus tau xz. And this is how z momentum is transported in y direction, that will be equals to rho vy into vz, that will be equals to plus tau yz. Now already we have discussed, okay, so which are 0 and non-zero. So in this term, this rho vz plus pz, okay, not pz, rho vz plus p is a non-zero term, okay, here, because here velocity is not changing in z direction, that is why this is equals to 0. So this is non-zero, this is non-zero. In this term, this is 0 because we don't have velocity in x direction, and this is non-zero because I have velocity in z direction which is changing in x direction. So this is non-zero. Again in this term, okay, in this term, so this is 0 because I don't have velocity in y direction. So this term is 0, and I don't have velocity in y direction, and velocity z velocity is not changing in y direction. So this is also equals to 0. This in detail we have discussed, and this is the gravitational force. Okay, this is the gravitational force. So what will be the forces acting in the direction of flow? So flow direction is Vz. So what is the force acting because of gravity in a direction of flow? So if say here the direction of gravity is z, so gravitational force is z g in this direction, g capital small g, acceleration due to gravity. So that will be gravitational force. Okay, using that I can get the gravitational force. So how to get a gravitational force in a direction of flow? So this z direction, what will be the gravitational force in z direction? Anybody in the class?
G cos beta.
Yeah, g cos beta, because here g and our horizon, this vz is in direction of beta. So this acceleration due to gravity in a direction of flow. So that will give you a forces. Okay, acceleration due to gravity. Here only flow is because of gravity. Okay, pressure difference is not playing much role. So whole flow is because of gravity only. So only that force we are considering. So force because of gravity. So in a direction of flow, acceleration due to gravity is z. And how to get force from this gravity, acceleration due to gravity? Yeah, how to get force? There roll number 25, Nivas. Roll number 25, Nivas. Roll number 49, Harshavardhan.
Yes, sir.
So acceleration due to gravity in a direction of flow is g cos beta. So what is the forces because of this gravity in a direction of flow? Force.
Sir, density times g cos beta.
Okay, density. So density multiplied by acceleration due to gravity will be force.
Sir, into length into width.
Width, length into width into density into acceleration due to gravity. That will give me force.
Sorry, sir. It will be density times volume into g cos beta.
So what is that density times volume?
Sir, volume will be
No, what is
L.
density into volume?
Density into volume is mass.
Yeah, force is mass into acceleration. Okay, this is well-known physical equation actually. So density, force is mass into acceleration. So mass of this differential shell is, so length L, width W, LW into delta x. This is delta x. This delta x I am talking about. Okay, this delta x, that will give you volume multiplied by density will give you mass, and multiplied by acceleration due to gravity in a direction of flow, that will give you force acting because of gravity. Okay, so overall why we have discussed this flux. So using this flux we can get a rate of momentum coming in, rate of momentum going out. Okay, so for that we have discussed flux from last 20 classes. So fluxes we are discussing from 20 classes, because fluxes will be used to get the rate of momentum coming in, going out. And these are the total forces, other forces acting on gravity. This is equivalent to generation and consumption of momentum. Okay, here momentum is generated because of this force. There is no consumption. Okay, consumption is considered here actually. So generation and consumption will be all forces acting externally. External agency, whichever be the forces acting on my system, that is equivalent to generation and consumption. And so accumulation is zero, because I am considering steady state. So this we have discussed. Now we will put into equation form. So this is what generalized Newton's law of viscosity. One by one we will discuss, which is zero and non-zero. This is already we have discussed. Just we will repeat. So tau ij, this is generalized Newton's law of viscosity, because we are handling liquid. So in compressible flow, density is constant. So density is constant. So this bracket is zero. So this bracket is zero. So tau xj, tau xz as velocity, this is non-zero, tau xz, because vz is changing in x direction. Okay, vz is changing in x direction, vx equals to 0. So this is 0, this term is non-zero. Okay, this will be equals to minus mu dvz by dx. Similarly, so tau xy, so this will be a 0, because vz is not changing in y direction. First of all, there is no variation of vz in y direction, and y velocity is equals to 0. This is 0 because vz is constant in y direction, and this is 0 because vy is 0 actually. So this will be equals to 0. Similarly, third will be a tau zz, tau zz, because this will be 0 and this will be 0, because vz is not changing in z direction. So only non-zero will be tau xz. Okay, non-zero will be tau xz. So tau zz will be equals to 0. So you can see this is whole 0. So I think this is the third or fourth time we are repeating. This tau phi yz will be equals to, this is convective flux and this is molecular flux. Both are 0. Phi xz is a convective flux is 0, but molecular flux is tau, given by, this is phi xz will be equals to tau xz, and this is a momentum flux in z direction. Okay, momentum flux in z direction. So this convective will be non-zero, this pressure will be non-zero, this will be 0. So this is non-zero term, this is non-zero term, and this is non-zero term. All other terms are 0. Now we can take a balance. A rate of momentum coming in the differential shell in z direction. How to get rate of momentum coming in z direction? A rate of momentum coming into differential shell in z direction. How to get that? Yeah, roll number 50, Rashmi.
Yes, sir.
Yeah, rate of momentum coming in the differential shell in z direction.
So coming inside Z direction will be uh,
So out of this six
that
arrow,
phi
this is
Z.
1, 2, 3, 4, 5, 6. which arrow I am indicating actually rate of coming in to the differential shell in Z direction. This is number 1, number 2, number 3, number 4, number 5, number 6.
So third one.
Third one, okay. So how to get this rate of momentum coming in this differential shell in this Z direction? So direction is correct. You have selected direction. Now how to get rate?
Sir, like coming inside will be at z equal to 0.
Yeah, phi ZZ. Okay, this is phi ZZ estimated at Z equals to 0.
So it will be phi zz at z equal to 0, rho vz square.
Rho V Z square. Rho V Z square. No, phi ZZ. That is flux actually. How to get a rate from flux?
So it will be W into delta x, sir.
W into delta x, that is perpendicular cross sectional area. Okay, this is phi ZZ at Z equals to 0 multiplied by this W into delta x. This is the cross sectional area perpendicular to this direction. And how about rate of momentum going out from differential shell in Z direction?
Sir,
Yeah,
it will
Rashmi?
be same, but at z equal to L.
Yeah, it will be this is the arrow which is indicating a flux at Z equals to L. Okay, in Z direction. So this will be a phi ZZ calculated at Z equals to L multiplied by which cross sectional area? This cross sectional area. This is W into delta X. This delta X I am okay. This delta X here differential shell. So this is the perpendicular cross sectional area that will give me rate of momentum coming in and going out in Z direction. How about in X direction? Roll number 52, Spandan.
Hello, sir.
Yeah, Spandan. Rate of
Sir,
momentum coming in the differential shell in X direction. I am discussing
it
X
will be,
momentum only. This is the balance for X momentum. But how X momentum coming in my differential shell in X direction?
sir, it will be 5xz at x equal to 0.
Not X equals to 0. My
No, sir,
differential,
x at x equal to x
yeah, at X equals to X.
and into the area perpendicular. That will be
What will be
L
area
into W.
perpendicular to that?
L into W.
L into W. This is the arrow which is giving me how Z momentum is flowing in X direction. How Z momentum is transported in X direction. So rate of Z momentum coming in this differential shell in X direction, that will be a flux in X direction multiplied by surface area. Okay, flux in X direction, Z X direction, Z momentum flowing in X direction multiplied by surface area. This surface area, this is L. Okay, this is L into W multiplied by phi xz estimated at X equals to X. Okay, and what will be rate of momentum going out from the differential shell in X direction? Spandan?
Sir, it will be same, but phi xz will be at x equal to x plus delta x.
Yeah. So phi xz. So this arrow will give me a rate of momentum going out from a differential shell in X direction. So it will be phi xz estimated at this surface. This surface is at X equals to X plus delta X multiplied by surface area is W into L. Okay. Roll number 53, Shivam.
Yes, sir.
So how about rate of momentum, Z momentum coming in my differential shell in Y direction?
Can you repeat, sir? Z
Rate
momentum
of
coming
Z
in.
momentum
Uh,
coming in my differential shell in Y direction.
in Y direction. Sir,
Yeah.
it will be 0, sir.
Yeah, but okay, it will be 0. You are correct. But can you give me just a formula which direction you are using and which surface area you are using?
Okay, sir. So surface area will be W into delta X
Can you
will be
just
the
think
surface
over
area.
this? Can you just
Yes,
think
sir.
over
What?
this? It is W into delta X.
Oh, no, sorry, sir. Not delta X. It will be L into delta X. Sorry.
Yeah, L into delta X multiplied by which component you
Multiply.
are talking about?
What, sir?
Component of momentum flux.
Sir, phi YZ.
Yeah. So you are talking about this arrow. Okay. So we are talking
Yes, sir.
about this arrow. This arrow is indicating how Z momentum flowing in my differential
Phi.
shell in Y direction.
Yes, sir.
This is Z momentum coming into my differential shell in Y direction. This is at Y equals to 0. Phi yz at y equals to 0 multiplied by surface area of the surface which is perpendicular to this arrow. What is the
Yes, sir.
surface area? It will be L
L
into
into
delta
delta X.
x. Okay. And what will be rate of momentum going out in y direction?
Same, but at phi YZ at Z equal to L.
Not z equals to L.
Z
You are
equal to
confusing
W, sorry.
actually.
Y equal to W.
Y equals to W. So this is the surface at y equals to W. And which surface area? Surface area will be
L into delta X.
yeah, this is very important actually. You will be always considering perpendicular surface area. And these three component, how to discuss this three component, this we are discussing from first class itself. This is indicating Z momentum and this is indicating in which direction this momentum is transported. Okay, but
Yes, sir.
effectively this is equals to 0. Okay, 0, this will be equals to 0 because both terms are 0. 5 iz equals to 0. So this is equals to 0, this is equals to 0. So only two rates are in x direction and in z direction. Okay, in x direction how z momentum is flowing and in x direction. So this is what and already we have discussed generation and consumption of the momentum will be total forces acting on this differential shell. This volume of differential shell will be delta x. So this delta x multiplied by length multiplied by width will give me volume of this differential shell. Volume multiplied by density will give you mass of this differential shell. Mass multiplied by acceleration due to gravity will give me a forces acting on this surface. That will give me a rate of generation and consumption of the momentum. So you know that now. So how why we can compare this rate of this forces with the rate of momentum? So rate of momentum can be interpreted as a flux force. This already we have seen. Okay, momentum flux is a shear stress. Shear stress multiplied by area is a force. Okay, so we are taking a momentum balance. Okay, momentum balance or a force balance you can say. This is force balance or momentum balance. So rate of momentum coming in minus rate of momentum going out plus generation of momentum, rate at which momentum is generated and rate at which momentum is destroyed or consumed. So that will be a total forces acting on a my differential shell by external agency, any external other than this. Okay, other than viscous forces and this thing. Okay, so whatever external forces acting on this, here it will be a gravitational force. So it will be g cos of beta multiplied by mass of this differential shell. Mass will be a volume multiplied by density. Okay, this is what we will put into this equation. So this will give me a rate of momentum coming in. So this we have combined this rate of momentum coming in minus rate of momentum going out. Combine, we have combined this. Okay, in all direction plus forces of gravity acting on a system. This will be a generation and consumption. This is equivalent to rate of generation minus rate of consumption of the momentum. That equals to 0. Overall shell momentum balance will be equals to rate of momentum coming in minus rate of momentum going out plus generation of momentum minus consumption of momentum equals to accumulation. This is overall shell momentum balance equation. So it is very easy to visualize mass balance equation. Rate of mass coming in minus rate of mass going out plus generation of mass minus consumption of mass equals to accumulation. This is overall mass balance equation. Exactly, this is the equation moment in momentum balance. Rate of momentum coming in minus rate of momentum going out plus generation of momentum minus consumption of momentum, which is indicated by total forces acting on a system. Okay, here only gravitational force is there. If other forces are also there, so if I am using pump or something, so that will be accounted here. That will be accounted as the generation and rate of generation of momentum, rate of consumption of momentum, and that will be equals to accumulation. And accumulation term is 0 here because we are considering steady state. There is no variation of property with respect to time. Hence, accumulation is 0. Okay, accumulation of momentum in my differential shell is 0. So this is what overall rate shell momentum balance equation is there. So rate of Z momentum coming in across the surface at Z equals to 0. Rate of Z momentum coming in my differential shell at Z equals to 0. Okay, rate of Z momentum coming in Z direction. Okay, that will be equals to phi ZZ at Z equals to 0. That will be phi ZZ at Z equals to 0 multiplied by perpendicular surface area is W into delta X, this surface area. I am talking about this arrow. And this is the surface area. This is the surface area. Similarly, rate of Z momentum going out in Z direction. Okay, rate of Z momentum going out in Z direction from my differential shell, and that will be equals to at Z equals to L. Z equals to L. This is the arrow I am talking about. So how to get this? This will be a phi ZZ estimated at Z equals to L. Phi ZZ estimated at Z equals to L multiplied by perpendicular surface area. This will be width into delta X. Similarly, this will be a rate of Z momentum coming in my differential shell in X direction. So I am talking about this arrow. Okay, I am talking about this arrow. Rate of Z momentum coming in my differential shell in X direction. Okay, in X direction, that is at X equals to X. Okay, any value. This will be a differential starting point of a differential shell X. Okay, that is variable. So that will be a phi xz estimated at X multiplied by surface area is this surface area. Okay, this surface area will be this length multiplied by width. Similarly, rate of Z momentum going out. Okay, rate of Z momentum going out from my differential shell in X direction, that will be at X plus delta X. So I am talking about this arrow. Okay, I am talking about this arrow. That will be equals to phi xz estimated at X plus delta X multiplied by surface area will be this length into width L into W. So this is what rate of Z momentum going out across the surface at X plus delta X. Okay, perpendicular surface area I am talking about. Okay, all fluxes I am taking and perpendicular surface area to that flux. Okay, so that is why it is very important to align your axis and origin along the boundaries, okay, along the boundary of your system, so that this taking perpendicular surface area, discussing fluxes direction will be very easy. Okay, so this is an rate of Z momentum coming in across the surface at y equals to 0. So this is what I am discussing. Okay, rate of Z momentum coming in my differential shell across the surface at y equals to 0. So that will be equals to phi y z multiplied by surface area will be a length into delta s, and rate of Z momentum going out. So this arrow and this arrow, this equals to 0. Okay, this is 0. So this is overall, and this is rate of momentum coming in Z direction. This is rate of momentum coming in X direction. This is the rate of momentum going out in this is rate of, okay, this is rate of momentum going out in Z direction. This is rate of momentum going out in x direction plus total forces acting on a system. Okay, gravitational force acting on a system, that will be a, so g, so this will be g, and the acceleration due to gravity in this direction will be g cos of beta. Okay, g cos of beta. So this is g cos of beta is a acceleration, and this will be a L into W into delta x into density. This is a mass of a differential shell. This is mass of a differential shell. This is volume of a differential shell. Volume multiplied by density will give you mass. Mass into acceleration will give me a forces. Okay, forces acting on my differential shell because of gravity. Now, just read this slide and let me know if you have any doubt in this slide. Okay, this is very important. Okay, very important. Which area you need to take, which component we need to take. So we have not taken y direction and all. So hope everything is clear to everybody. If you have any minute doubt also, just let me know. Now I can take a balance of this. So this will be a rate of momentum coming in, this plus this. This is rate of momentum coming in, this is rate of momentum coming in, and rate of momentum going out will be this plus this. This will be a rate of momentum going out. So rate of momentum coming in minus rate of momentum going out plus generation and consumption of the momentum, rate at which momentum is generated and consumption, that is nothing but the forces. So this forces, that equals to 0 for steady state. Okay, so this is rate of momentum coming in. So we have combined this. Okay, this is rate of momentum going out plus generation and consumption of the forces, that equals to 0. That equals to 0. Substituting this here. Okay, this is rate of momentum coming in minus rate of momentum going out in z direction. This is rate of momentum coming in, not z direction, this is x direction. This is the rate of momentum coming in minus rate of momentum going out in z direction. That will be equals to total forces acting on a system. Here only gravitational force is there, gravitational force. So that will be, this is volume multiplied by acceleration, volume multiplied by density, that will give you a mass, mass into acceleration, that will give me force, that equals to 0. Now hereafter, physics of the problem is over. Now hereafter, only mathematics is remaining. But your role is very, very important for getting this equation. Hereafter, you can solve this equation even if you don't know transport phenomena, you don't know fluid mechanics. So even though you can solve this problem, once you get this equation, getting this equation is a momentum transfer. Okay, getting this balance equation is a momentum transfer. Hereafter, if you are very expert in mathematics, you can solve it very easy. Okay, hereafter, everything is mathematics. Okay, hereafter, there is no momentum transfer. Hereafter, there is no fluid mechanics. Hereafter, it is mathematics. So if you are expert in mathematics, so getting this equation is very, very important. So all assumption, there should be logical assumption. So all dimensions, what you are taking, coordinate system you are taking, origin you are taking, which are zero, non-zero, which fluxes are important, that you need to decide. That is what engineering is there. Otherwise, hereafter it is just a mathematics. So what can be done? Now you can see, you have x plus delta x and x. This is property estimated at x and this is property estimated at x plus delta x. So certainly you will be getting a differential equation for this phi xz. Okay, and so now I can substitute this phi xz and phi zz and see, substituting this phi xz. So first of all, divide by L into delta all constant. Okay, divide by all constant into differential thickness. Okay, this is what procedure, you can say, mathematical procedure. You divide by volume, here volume, otherwise all constant multiplied by a differential thickness, all constant. So here L is a constant, width is a constant. So divide and multiply it by -1 and rearrange the equation. Okay, so divide by constant into differential thickness multiplied by -1 and rearranging the equation. Everything is done so that we can get easily a differential equation of x. All this manipulation is done so that we can get a differential equation for x. Now after dividing this, okay, L into W into delta x, do it, okay, do it on your own, okay, divide it by L into W into delta x, this term, and this term, multiplied by -1 and rearrange the equation. Just see what equation you are getting. Here, roll number 68, Mitu.
Yes, sir.
So what is the equation you are getting?
So like we have divided by LW delta x and then multiplied by -1. So the first term we are getting that 5xz at x equals to x minus 5xz at x equals to x plus delta x. That will be divided by delta x, and then second term will be divided by.
Are you writing or just orally you are telling?
No, sir, I am writing.
So where is then -1 multiplication gone?
Yes, sir. Sir, in that second term, that 5zz equation will be multiplied by minus.
This will be also multiplied by -1, na?
Yes, sir. Yes, sir. That terms will get interchanged. And sir, in the second equation, we will have minus sign, and that overall equation will be divided by L.
Okay, very good. So I request you to revise all the differential equation, all rules for plus minus, all rules for bracketing and everything. Okay. So whatever you have studied mathematics till now, that revise everything. That will be useful here. You are not studied just mathematics for fun. Okay. So and that I am not going to cover in this transport phenomena. Hereafter, so sometime I will say that okay, this problem is finished. Transport phenomena is finished. Hereafter, just mathematics. So mathematics, you are studying it from say last 4-5 years actually. Important mathematics. Okay. So this is the equation I will get. This phi xz at x plus delta x minus phi xz at x divided by delta x minus phi zz at z equals to 0. Okay, this is minus. This you can see this is minus. Okay, this -1 is coming here. Phi zz at z equals to 0 minus phi zz at z equals to L divided by L equals to rho g cos of beta. Rho g cos of beta, and this minus was there, but here side is changed. So hope everybody is getting this equation. Anybody not getting this equation? Okay, now if delta x tends to 0, so I can use the definition of differentiation. The property at x plus delta x minus property at x. Okay, a property, this is any property at x plus delta x, f at x plus delta x minus f at x divided by delta x, and delta x tends to 0. So this will be a differential of df by dx. Okay, this you know, and this is what you will get. Okay, definition of differentiation. Okay, property at x plus delta x minus property at x divided by delta x. Limit delta x tends to 0. That will be equals to del by del fx. Del by del x of phi xz. Okay, this is the definition of derivatives. So I can substitute it here. Okay, I can substitute here delta x tends to 0, and I can substitute the value of phi xz, phi zz at z equals to 0 and phi zz at z equals to L. Okay, substituting. Okay, this will be a phi del by del x of phi xz minus phi zz at z equals to 0 minus phi zz at z equals to L. That will be equals to rho g cos of beta. Now you substitute this phi xz and phi zz. Okay, phi xz will be equals to, already this equals to 0. Okay, phi xz will be equals to, this is uh, um, molecular momentum flux and this is the convective momentum flux. Molecular momentum flux because of pressure forces will be 0 for phi xz. So this will be 0 because Vx equals to 0. Only non-zero term is this, or you can call it as a tau xz. Tau xz or minus mu dvz by dx. Okay, this is the non-zero term. Here phi zz, so p plus tau zz plus rho vz. So again this will be equals to 0 because there is no variation of velocity in z direction. Vz is not varying in z direction. So this is non-zero, this is non-zero. So I can substitute both here and rearrange the equation. Okay, rearrange the equation. So you can substitute here p. Okay, so p plus vzz at z equals to 0 minus p plus rho vzz at z equals to l. What is that value? Here roll number 76, Atharva. Roll number 76, Atharva. Roll number 77, Tejas.
Yes, sir.
Yeah, just discuss about this term. Okay, p at z equals to 0 minus p at z equals to l. What is that equals to? Whether pressure is changing in L z direction.
Mm,
P at z equals to 0 and P at z equals to L. This term, whether pressure is changing in z direction.
Yes, pressure and tau z. P minus 2 mu dvz by dz plus rho z vx.
Anyway, this equals to 0. Why this is equals to 0, Tejas?
Because it is not varying with z direction.
Okay. So pressure at z equals to 0 and pressure at z equals to L. Whether it is changing or it is different.
Constant.
P at z equals to 0 minus P at z equals to L. What is that equals to? This pressure at z equals to 0 minus pressure at z equals to L. What is that equals to?
0.
0. That is what I am asking. Again, rho vz square. Now this is already 0.
Yes.
Okay. Rho vz square at z equals to 0 minus rho vz square at z equals to L. What is that
0.
equals to?
0.
Yeah.
0.
Why?
Because vz. No, it will be rho vz square.
Vz square at z equals to 0 minus rho vz square at z equals to L. What is that
Minus
equals to?
minus rho vz square.
Minus rho vz square. So here rho vz square at z equals to 0 and minus rho vz square at z equals to L. Velocity changing in z direction.
No, it's 0. Vz is 0.
So it means
That is
that
not varying
phi
in z
zz
direction.
at z equals to 0 minus phi zz at z equals to L. What it will be equals to?
0.
0. So this term is 0 actually. Isn't it?
Yes.
Anybody has confusion? Similarly, if we consider a X momentum balance and Y momentum balance, this was the non-zero term in there. And this will also, I will get a 0 equals to 0 or P equals to P or tau ZZ equals to tau ZZ. That is what we will be getting if we do a shell momentum balance in X direction or X shell momentum balance equation and Y shell momentum balance equation. If you remember, so we have neglected this. So what I am talking is you just concentrate phi, Z, X and P. This is what I am talking about. So where is that? Okay, this here. So even though this tau xz here, you can see tau xz is non-zero and P is non-zero here, P is non-zero here, still we are not considering X momentum balance equation and Y momentum balance equation. If you take this X momentum balance equation and Y momentum balance equation, either you will get 0 equals to 0 or tau zx equals to tau zx or P equals to P. That is what you are going to get. Okay, so that is hence shortcut is if I don't have X momentum, don't consider X momentum balance. If I don't have Y momentum, don't consider Y momentum balance equation. I have only Z velocity, hence we have considered only Z momentum balance equation. This is clear to everybody? Anybody has any doubt? So what final equation I will get? I will get d by dx of tau xz. That will be equals to rho g cos of beta. Now I can get the model equation which will give me a flux profile by solving this differential equation. Okay, by solving this differential equation, I can get a flux profile, provided I should have at least one boundary condition available. Then I can get a flux profile for that. So whether that boundary condition is available, flux boundary condition. So flux should be given at some boundary with respect to x only. Now I don't have differential equation in y direction, I don't have differential equation in z direction, it is the differential equation in x direction at some value of x. If flux is given, so I can solve this differential equation and get the flux profile. So profile equation is nothing but the equation which is defining the variation of flux at different location. So whether I have flux boundary condition here,
Yes, sir.
whether I have flux boundary condition here.
Yes,
So
sir. We
what are
have
the
no
boundary
slip boundary
conditions
condition.
available for this problem? The roll number 91 Shubham.
Yes, sir.
Whether I have flux boundary condition.
Flux boundary condition. Yes, sir.
So what is that flux boundary condition?
Sir, can you show the figure?
Yeah.
Sir, at x equal to 0, the length equal to L. Sorry, sir. At x is equal to L, flux equal to.
No, I want in x direction. Which is x direction? This is my x direction.
X direction. Sir, 1 minute. At the delta W, sir. At x equal to at x equal to LW.
LW.
Wait a minute, sir.
What are the boundaries of my film in x direction? It is varying from
W to 0 to W.
x direction.
0 to x, sir. 0 to delta x.
Not delta x. 0 to delta.
X plus delta x.
Not x plus delta x. Now I am talking about my film, not a differential shell.
Okay, sir. Then x. Then x, sir.
Yeah, x to delta.
X to delta. X2 delta, sir.
Figure actually. Yeah, Shubham, can you see my PPT now?
Yes, sir.
Okay, so what are the boundaries in X direction now?
Delta, sir.
X varies
X
from?
direction. X in X direction, delta, sir.
Okay, so where is flux given?
Flux given in XZ direction.
Okay, at which value of flux is given?
Which value of flux is given in XZ
Whether flux
direction?
boundary condition is given?
Flux boundary condition in XZ direction, sir. In ZX direction. ZX direction.
Okay, what is the flux at top surface of this film?
Top surface this with 0, sir.
Why?
Because all get cancelled, sir. Phi and
Are
P.
flux tau xz I am talking.
Tau
Tau
xz
xz at top surface.
at top surface tau xz equal to tau xz, sir. Rho g cos beta x.
Plus C1. Okay, this is integration. Okay, plus C1. So at top surface, can I estimate this tau xz? That is
Yes,
called
sir.
a modified no slip boundary condition. What is modified no slip boundary condition tells me this top surface is the interface of gas liquid interface. So here I have gas and here I have liquid. So what is at x equals to 0 value of tau xz?
0 C1, sir. Constant.
How it is C1? It will be equals to 0. This
No,
we
sir.
have
Constant,
discussed.
sir. We have integrated now, sir.
Yeah, we have
It's not a
integrated. We have integrated, but tau xz equals to 0 at x equals to 0.
Okay,
Why?
sir. With constant also 0. At
No,
x
no,
equal
no,
to
no. No, 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 no. That is giving me constant equals to 0.
that is only talking as sir. We will get
Okay,
constant equal
that
to
is
0.
giving me constant equals to 0, but tau xz at x equals to 0 is 0. At this surface, tau xz equals to 0. What is the reason?
No slip boundary condition.
Not no slip boundary condition. No slip boundary condition is at this surface. At the bottom
Because
surface, at x equals to delta.
we store the water because of that.
Yeah, that is modified no slip boundary condition. Okay, no slip boundary condition is at x equals to delta.
Delta.
So this is x equals to 0 and x equals to delta is no slip boundary condition. X equals to 0 is modified no slip boundary condition. What is that modified no slip boundary condition? Not modified no slip
Tau
boundary.
x,
Yeah.
tau x equal to
Modified
0.
no slip boundary condition, gas liquid interface.
Gas liquid interface. Okay, sir.
Flux will be equals to 0. Why?
Flux equal to 0 because modified boundary condition.
Why? What is the reason?
Sir, because all get cancelled, sir, while calculating.
Not all get cancelled, man. This I explained so many times. Anybody else remember what I told? This is zero flux condition. Okay. Gas liquid interface plus zero flux condition. at x equals to delta, at x equals to 0, at this surface, top surface, at this surface, flux equals to 0. Why? Anybody in the class remember?
The viscosity of gases is very less as compared to that of liquid.
Very
so
good.
the gases are not able to transport the motion.
Because there will be a continuity of flux first of all, and continuity of flux, on one side there will be a viscosity of gas, on another side there will be viscosity of liquid, and viscosity of gases are negligibly smaller as compared to viscosity of liquid. Hence, gases are not able to transport any flux in x direction at this top surface. Hence, effective momentum flux, okay, z momentum in x direction at this surface, gas liquid interface, will be equal to 0. That will be equal to this boundary condition, gas liquid interface. Okay, because at this top surface I have gas liquid interface and zero flux condition. Why zero flux? Because viscosity of gases are very smaller as compared to viscosity of liquid. There are not much logical explanation. There are only few. If you mug up all these 10, but you should be very precise. You cannot give one for other. Okay, logical this boundary condition. So you are telling it is 0 because it will get cancelled out. That is not the case. This is explained because viscosity of gases are negligibly smaller as compared to viscosity of liquid. So at top surface, the gases will not be able to give any momentum flux in x direction. That is why it will be negligibly small, and that will be taken equals to 0. That fluxes will be equals to 0. So that is the boundary condition. So at x equals to 0, tau xz equals to 0, that is giving me C1 equals to 0. Okay, substitute at x equals to 0, tau xz equals to 0. So that is what I am telling. This is first order differential equation. If I want a flux profile, I need at least one boundary condition. Okay, at least one boundary condition, and this is the boundary condition available with me. Okay, it is nothing to do with this equation. This at x equals to 0, tau xz equals to 0. Substituting this, I will get C1 equals to 0, and this is my flux profile. Tau xz equals to rho g cos of beta x. Why this is called as a flux profile? Give me the value of x, I can calculate flux. Okay, at x equals to 0, flux is 0. At x equals to 0.1, it will be a 0.1 into rho g cos of beta. At 0.2, it will be rho g cos beta into 0.2. At 0.3, it will be linear. It is linearly varying. This flux is linearly varying for this case, where delta is smaller. Delta is smaller. That is what assumption is there for this case. So this is the flux profile. Once I get a flux profile, here I will use a, now I will substitute Newton's law of viscosity here. Substituting Newton's law of viscosity. What is Newton's law of viscosity? This is what flux profile is there. Okay, you can see here flux is 0, tau xz, and it is increasing, and maximum flux will be at the bottom. So what will be the maximum value of flux? That will be a rho g cos of beta into delta. Okay, that will be a shear stress exerted by flowing fluid on a plate. Shear stress exerted at x equals to delta. So at here shear stress will be 0, and here shear stress will be maximum. That will be equals to rho g cos of beta, and here delta. Okay, delta. That will be a this thing. Okay, flux profile. Okay, once you got a flux profile, so how to get a velocity profile? Anyway, before closing this class, there is an announcement. So we'll continue this class today at 2 o'clock also, because we have missed 4 classes, 2 initial classes and 2 during your GATE exam. These 4 classes need to be compensated. Okay, makeup classes will be there for these 4 classes before midterm exam. And in that first makeup class will be at today 2 o'clock. Okay, at today 2 o'clock there will be a makeup class, and we'll continue this discussion. So anybody got any problem? So this is my flux profile, and this is the pictorial representation of flux profile. How flux is not changing, how flux is changing in x direction. Why this arrow is not given to flux profile? Anybody can give the logical reason. Okay, this is the intensity of flux profile. This is the magnitude of flux profile at this value. So at this value, this is the magnitude of flux profile. At this value, this is the magnitude of flux profile. Only magnitude is plotted. Why arrow is not given to flux profile? What is the basic representation when arrow is indicated? It is indicated with arrow.
When represented by arrow, it is a vector that is with
Yeah, very
magnitude
good.
and
Whenever I have vector, it will be represented by arrow. Okay, arrow indicating me that I am discussing a vector properties. While this momentum flux is not a vector property. Okay, this is a tensor. This is neither a vector nor a scalar. It is tensor because two directions are associated with this. Actually, two directions are associated with this. This arrow, okay, this arrow is indicating x momentum. Okay, but tau xz, this is how tau xz is plotted. Okay, this it is giving me just a magnitude. Okay, magnitude of tau xz. Okay, this is the flux profile. So we'll continue our discussion for getting a velocity profile and other property at 2 o'clock today. Anybody has any confusion till this? Okay, then thank you very much. So we'll continue our discussion today at 2 o'clock. You use this Friday's class link for joining the class at 2 o'clock.